Okay. Uh, can everybody hear me okay? All right. Okay. Hmm. All right, good. Right. So here's where we were last time. We finished talking about configuration and we started talking about velocity. And we just talked very quickly about a simple velocity of a particle, and there was nothing exotic about that. And then I sort of suggested that if we want to talk about velocities of rigid bodies, we need a more sophisticated idea about what I have no idea why my here sorry, we're going to need a more sophisticated idea about what velocity is. And so this induced us to introduce the notion of a tangent vector, and I'm definitely not going to go through the entire construction again, but the idea is that if you have two curves, gamma 1 and gamma 2, and they both pass through the same point x, so here's gamma 1 like so, and here's gamma 2 like so, then we say that these are equivalent when if we represent the curves in a chart, which is what I'm doing down here. Okay, so I have a chart domain U and then a chart map phi. And then these curves, which I call, well, I don't call them that, they just are, phi composed with gamma 1 and phi composed with gamma 2. That when I represent them down here in Rn, okay, these now are things that we are comfortable with. Okay, these are curves in Euclidean space, and so they have well-defined tangent vectors, which is simply the if the curve passes through the point phi of x, which is that point there, at time 0, and that's what it meant, remember, to be a curve at x. Then the velocity we understand is just the derivative, okay, and that's the derivative, okay, and then equivalence of these two curves means that they have the same derivative at time 0, okay. And so a tangent vector was an equivalence class under this equivalence relation, that when you represent the two curves in a coordinate chart, the standard vector calculus tangent vectors agree. Okay. All right. And then once we had tangent vectors, we could talk about the tangent space, which is at x. Okay. So the tangent space is defined at a given point, and it's simply the collection of all tangent vectors. Okay. And then the tangent bundle is the union of all the tangent spaces. Okay. So we're going to talk about this at some length over a period of lectures. So let's just get to it. Okay. Let's look at a very simple example just to kind of anchor this. The example's maybe not a good one because it's kind of too simple, but it kind of allows us to get started, and then I'll say some more interesting things about tangent bundles, and then I'll sort of talk about an example which shows you that things aren't as simple as they are in this example. Okay. All right. So we're going to consider, what's always thought of as the simplest example of a manifold, which is simply an open subset of some Euclidean space. Okay, so that has a single chart, which is just U, and then the chart map is just the inclusion mapping, or the identity mapping U into Euclidean space. Okay, so open subsets of Rn are manifolds in obvious ways. Okay, all right. So let's think about, let's take a point X in U, okay? And let's think about what a tangent vector at X looks like, okay? Well, the definition of tangent vector says it's an equivalence class of curves. So choose a curve. Gamma at x. Okay, so remember, a curve at x by definition has the property that gamma of 0 is equal to x. Okay, so it passes through x at time 0. All right. Now, because we don't have to do this business with charts that we did up here, because we're already in an open subset of Euclidean space, we can we kind of know what the tangent vector of gamma is. Okay, so the usual tangent vector associated to gamma at time 0 is simply d gamma at 0. Okay, and so let's call that vector a vector v. Okay, so the picture here is very simple. So again, because our manifold is already sitting in Euclidean space, that sort of simplifies the generalities, because we have the natural kind of identity chart. Okay, so here's our subset U, and we have a curve gamma which goes through there, and it has a tangent vector d gamma at 0. Okay, now but a tangent vector isn't one of those. A tangent vector is an equivalence class of curves. So it turns out that every tangent vector, and so this is the thing we're calling v. Okay, so it turns out that every tangent vector at x has an obvious representative in its equivalence class. Okay. And so let's make sure that we understand what all those words mean, okay? Because a tangent vector, after all, by definition, okay, a tangent vector is an equivalence class of curves, okay? So what I'm telling you here is that if I give you a tangent vector, meaning an equivalence class of curves, that among all those curves, which are equivalent to the one you chose, so the one here I'm calling gamma, there's a one representative which is kind of obvious. All right, so let's make sure. I think if if I forced you to spend a few minutes to think about this, you would guess what that curve was. Okay, so but I'll just tell you. Okay, and I'll call this curve gamma x comma v. Oh, sorry, not t. V. Okay, and this curve is simply, okay, so it's a curve, and so what should this curve do? It should pass through x at time 0, and it should pass through x with velocity v. And so like I said, there's an obvious choice of such a thing, and it's simply x plus t v. Okay, so that simply is the straight line curve. Okay, and that has a tangent vector here, v. Okay, and so notice then that we have a natural way of thinking of tangent vectors at x, so elements of the tangent space at x, as being in Rn. Okay, and the Rn that I'm talking about here is that one. Okay, it's where V lives. Okay, so in other words, there is a natural bijection, okay, from the tangent space at x to u with Rn. Okay, and let me sort of explicitly write down what that thing is. Okay, on this side, I have a tangent vector, which is an equivalence class of curves, and on this side, I have a vector in Rn. Okay, so the equivalence class, the curve that I'm going to talk about, whose equivalence class that you want to take is going to be this one. Okay, and so it's going to be the equivalence class, and so I'm using the square brackets notation for equivalence class. Okay, so the equivalence class of the curve gamma xv under this bijection just maps to v. Okay, all right. And so in this case, we understand the tangent spaces pretty well, and moreover, oops, we also have and I'm writing bijection now. We're going to see that this is more than just a bijection. So we also have a bijection from the tangent bundle at u, okay, to u cross Rn. Okay, and this bijection is really just this one, except the only difference now is that I allow, here I thought of x as being fixed, and here I'm going to think of x as being variable. So I have the same thing. So it's going to take gamma x v, except now, because I'm thinking of x as not being fixed, but as being variable, it's going to map it to x v, like so. Okay. All right. So, so that example, like I said, that example is maybe too simple because, and that's deficient in two different ways. It's deficient because if this is what I'm going to do, then this seems like an exceedingly complicated way of doing something that's kind of obvious, which is defining tangent vectors to curves in Rn. Okay, so that's one way in which it's defective. And then the other way in which it's defective is that it gives us this kind of an identification of this space with this space, and it leads us to thinking that tangent bundles are simple things, and tangent bundles are not necessarily simple things. Okay, so we'll work our way towards that, but for the moment, let's do the following thing. Okay, and that is we're going to show that the tangent bundle of a manifold is a manifold. Okay. And you know we're going to do this and not just in some sort of arbitrary way, because you know, as you've seen from your homework problems, you know, if I just give you a set, like for example TM, it doesn't necessarily, it can possess weird manifold structures, but when I say it's a manifold, I mean given a manifold structure for M, there's a unique one that gives rise to the manifold structure for TM. Okay, and so in particular, if M is n-dimensional, okay, and so we know what n-dimensional means. It means all charts take their values in Rn for some fixed n. What do you think the dimension of the tangent bundle should be? Maybe this is a good example to think about to try to guess what the answer might be. 2n is correct, okay? All right. Okay, so let's do that. All right. So what we will do is we will build an atlas TA for TM given an atlas A for M. Okay, and remember to show that something's a manifold, that's all you need to do is to build an atlas for it. Okay, and we'll see that as we do that, this property will naturally be satisfied. Okay. All right, so first thing we'll do is we'll say how to, if I give you just a chart for M, how that induces a chart for Tm. Okay, so first, let U phi be a chart for M. Okay. All right, so we define a chart for Tm, and I will denote that chart by Tu T phi or Tm. Okay, and here's how you define Tu and T phi. All right, so Tu, all right, so remember that Tm is the tangent bundle by definition. That's the union of all the tangent spaces. And so to define Tu, I'm simply going to take the tangent spaces, not over all of M, but just over U. Okay, so Tu is the collection of all tangent spaces at X for points X and U. All right, and T phi. Okay, so T phi, it's a chart whose chart domain is Tu, and so it certainly has to have domain Tu, and so its domain is going to be Tu, and it's going to map into phi of U cross Rn, and that's going to be thought of as being a subset of Rn cross Rn, which is R2n. Okay, and so you can see here then that if charts for M take, oh, sorry, I should be clear about that. Where phi is a map from U into Rn. Okay, I need to say where what n is. So n is the Euclidean space in which phi is the dimension of the Euclidean space in which phi takes its values. Okay, and so you can see here that if your manifold is n-dimensional, then the tangent bundle is going to be 2n-dimensional. Okay, so I need to tell you what T phi is defined. Sorry, what T phi is. Okay. Okay, so T phi. Okay, so T phi is going to take a point in Tu. Okay, and a point in Tu is an element of some tangent space at a point in U. Okay, so what I know then is that this is going to be an equivalence class of curves. That's what a tangent vector is. So it's going to be an equivalence class of curves at some point x. Okay, and so to be clear, this is an equivalence class of curves at x in U. Okay, so I know that every tangent vector in TU looks like this for some x. All right, so now I need to tell you what this thing does in terms of what it looks like in phi of U across Rn. Okay, so it's going to do the obvious thing in the first component. It's going to be phi of x. Okay, and then in the second component, it's going to be, well, again, it's kind of going to be obvious if you think about the picture here. Okay, about what it means to be a tangent vector, and the velocity when we represent that in coordinates is just this thing. So that's what we're going to use for the second component of a tangent vector. So we go d phi composed with gamma at 0. Okay, so that's t phi. All right, so we need to show first that t phi is a bijection onto an open subset of R2n, right? Because that's the first property of a chart, is that it has to be a bijection onto an open subset of whatever Euclidean space it is that you're dealing with, okay? So indeed, T phi of Tu is equal to, okay? So let's first consider what the image of T phi is, okay? And the image of T phi is simply going to be phi of U cross Rn, okay? And this is an open subset in R2n. Okay, so first the image is that. Okay, now why is that? All right. So what I need to do, so to see this, let x. Okay, so if I were using my LaTeX word processing program to write this, I would write x for points in the manifold, and I would write bold symbol x for points in Euclidean space for vectors. But since I sort of don't have access to that, I will occasionally, but not very often, when I want to emphasize the difference between points in a manifold and points in Euclidean space, I might do that by putting like a bar underneath them or something to work, some kind of vector-y kind of notation. Okay, so I'm going to take a vector in here. Okay, what I need to do then is I need to show that there exists a curve, okay, at x, okay, and so x here is going to be phi inverse of x bar, okay, and I need to show that there's a curve gamma at x, so that phi of x is equal to x bar, and so the d phi composed with gamma of x is equal to v bar. Okay, that's what I need to show that that's the image. Okay, then let gamma x v be a curve, or sorry, be the curve in at x in M. Okay, so gamma is a curve in M now, and so it's similar to what I did up here. Okay, where I define this curve gamma, xv. Okay, but here I'm in the manifold, not in an open subset of Euclidean space, but it's the same idea. Okay. And I define gamma xv to be the curve with this property, so that phi composed with gamma xv of t is equal to x bar plus t v bar. Okay, so in other words, what I'm doing is when I represent the curve gamma in the chart phi, I get this curve that I talked about in the example above. Okay, all right, so then it's clear then. You just have to check it explicitly. Okay. All right, so that shows that the image is open. And moreover, it tells you exactly what that image is. It's the chart domain phi of u, or sorry, the chart codomain phi of u in the first component, and it's all of Rn in the second component. Okay, sort of corresponding to the fact that I can achieve arbitrary velocities as I pass through the point x. Okay, now I need to show that it's bijection. Okay, so I'm not going to carefully go through this. It's not difficult, but you have to think a little bit about this. And really, what it amounts to is it amounts to showing that there's always going to be a unique x bar and v bar for which. Okay, so to show, so I'll just write out the idea. To show that T phi is a bijection, one can show, and again, it's just explicitly you can show it just by computation. One can show that if gamma x is in TU, then there exists a unique x bar, v bar, in phi of u cross Rn, okay, such that phi of x d phi n 0 equal to x bar v bar. Okay, and the idea is really, we've already seen it when we looked at this example up here. Okay, when we had this bijection that we talked about up here, that's exactly going to give you the uniqueness here. Okay. All right, so that's part one of showing. Sorry. So this establishes. So this establishes that TU T phi is a chart. Okay, but remember what I'm trying to do here is I'm trying to show actually that if you have an atlas for M, then you get an atlas for TM. Okay, so now I need to work with the overlap condition. Okay. Now suppose all right, so I have a bunch of charts. Okay, we claim that TA, which is obviously going to be just the T's of all of these things, is an atlas. All right. And then you're done, because that's all you need to do to define a manifold structure is produce an atlas. Okay. So to show that this is an atlas, what do we need to do? We need to show that if you take two charts from here that intersect, okay, and so charts TUA and TUB, those are going to intersect if and only if UA and UB intersect, okay? Okay, so suppose that TUA intersect TUB is non-empty. Okay, so that means that the two charts intersect one another. That's the sort of starting point for the overlap condition. Okay, and this is true if and only if UA intersect UB non-empty. Okay, so we must verify the overlap condition. For TUA, TVA, and TUB, TVB. Okay, that and then we're done. Okay. All right. Okay, so what does the overlap condition mean? What the overlap condition means is that you have to represent points indicate how the representations in one chart are related to the representations in the other chart. That's the overlap condition. Okay. So we have. Okay, so the definition of T phi is phi b, sorry. Okay, so T phi b at a point, okay, is, this is just our definition of T phi b, so it's phi b of x, and then it's d phi b composed with gamma at 0. Okay. So what I need to do is I need to get the representation. So this is the representation of this is the representation of that tangent vector in this coordinate chart. Okay, what I need to do is I need to write the representation of this tangent vector also in the other chart, TUA, T phi a, and I need to see how it's related to that representation. All right, and so here's how we're going to do that. Okay, so we go T phi. Let me just Right, so it's going to be T phi A composed with T phi B inverse, right? So that's the overlap map, right? So remember the overlap map was when we did it initially, we had that it was phi composed with psi inverse. Okay, if we had two charts, U phi and V psi, the overlap map was phi composed with psi inverse. So we're just doing phi composed with psi inverse, where psi is equal to T phi B and phi is equal to T phi A. Okay. All right, so let's, I'm lecturing, I'll be with you in a second. Okay, and so what's this going to do? Well, this is going, first let's identify where this is a map to and from. So this is going to be a map from, okay, phi of, so phi B of UB cross Rn into phi A of UA cross Rn. That's what overlap maps do. So I'm going to write a point in here. I'm going to write that as X B V B, okay? And then a point over here, I'm going to write it as X A V A, okay? And the overlap condition, all it does is it just relates these two representations. Okay, so let's see if we can deduce what that is. Okay. All right. And so, okay. All right. So T phi A composed with T phi B inverse acting on X B V B. Okay. All right. So, well, in the first component, what's it going to do? So what's it going to do to XB? Well, it's going to do to XB what the overlap condition for phi B and phi A does to XB. Okay. And so that's just going to be phi A composed with phi B inverse of XB. Okay. And then what am I going to get for VB? Well, I'm going to be write what I want to do is I want to write VA in terms of VB. And what's that going to be? So that's just going to be D of phi A composed with phi B inverse XB. Okay, sorry, I'm going to move this onto a new line, or else I'll just bunch it up too much. Okay, so it's going to be D of phi A composed with phi B inverse at X A. Okay, so what's this thing? This is the Jacobian of this map. Okay, so I take this map, which is now a map from phi B of UB into phi A of UA, and takes the derivative of that, right? That's what this thing is. Okay, so this is just a matrix. What's the shape of this matrix? How many rows and columns does it have? What do you think? All right, so this is a map from phi B of UB into phi A of UA. Okay, so this sits inside Rn, and this sits inside Rn. So what's the shape of this matrix going to be? Right, n by n, right? Okay, so it's just the Jacobian matrix of the overlap map. Okay, so I take the Jacobian matrix and I evaluate, sorry, I apologize, I made a mistake. I'm evaluating it not at XA, but XB. That's okay. And so I take this n by n matrix and I hit VB with it. Okay. All right. So in other words, what I get that XA VA is equal to phi A composed with phi B inverse of XB, okay, and then D of phi A composed with phi B inverse of XB, matrix multiplication VB. Okay, so let's maybe think about how to justify that formula. Okay, right? So what I know is I know that VB is equal to D of phi B composed with gamma at 0, okay? Where, what's gamma? So where T phi B of gamma X is equal to XB VB. Okay, so gamma is the curve, which when I write it in coordinates is equal to that. Okay, so that's just the definition of T phi B. All right. Okay, so now let me sort of, actually, I think I want to start this. Yes, I'm sorry. I want to start with A, not B. A. Okay. And so this is phi A. Okay, so all I'm going to do now is I'm just going to slip the identity in there in the right place. Okay, so I'm going to write this as D phi A composed with phi B inverse composed with phi B composed with gamma at 0. Okay, so this is just the identity. So I've just written down a tautology. Okay, now I use the chain rule. Okay, the chain rule, remember, just says the D of phi composed with psi is D phi at psi of x composed with D psi at x. Okay, so the derivative at x of that. So that's the chain rule. So I'm going to use the chain rule. And what I'm going to do is I'm going to break this composition of 4 things down into 2 compositions, that one and that one. Okay. And so this is D of phi A composed with phi B inverse. Okay, acting on, okay, so what's the point here? The point here is going to be, all right, so the point psi of x here is going to be phi B composed with gamma of 0, but phi B composed with gamma of 0 is XB. That's the definition of XB. Okay. All right, so this is now going to be some n by n matrix. Okay, then I'm going to do matrix multiplication, just like in the chain rule, of D of phi B composed with gamma of 0. Okay, so this is also going to be a matrix. What's the shape of that matrix going to be? How many rows and columns will it have? Okay, so where's it a map to and from? Gamma is a mapping from R, okay, R1, into M, and then phi b is a mapping from M into Rn. So this thing is the derivative of a mapping from R1 into Rn, okay? So how many rows and columns does this matrix have? From R1 into Rn. So what's the columns? Is it one column or is it n columns?
One column.
One column is correct. I barely heard that, but I did hear it. Okay, so it's n by 1. Okay, so this is just matrix multiplication. But the point is that what's this thing right here? This thing right here, by very definition, is VB. Oops. Nope. All right, which is exactly what I set up here. All right. Okay, so that verifies the overlap condition. Okay. Oh, sorry, that doesn't verify the overlap condition. That just tells me what the overlap map looks like. Okay, so the overlap map looks like this. Okay, that's what the overlap map looks like. What we now need to understand is we need to understand that this mapping is a C infinity bijection, okay, with a C infinity inverse. Okay, so in other words, that it's a C infinity diffeomorphism. So finally, okay, so that's the overlap map. Okay, so I'm just going to talk my way through this, okay? So first of all, why is it a bijection? Well, the easiest, well, not the easiest, but one way to show that a mapping is a bijection is to demonstrate explicitly what its inverse is, okay? And in this case, this has an obvious inverse. And the obvious inverse is just obtained by swapping the roles of A and B. Okay, so if you write down the same mapping and you switch the roles of A and B, then those mappings will be inverses of one another. And so that gives you the bijective property. Okay, all right, so then all you need to do is you need to verify that this mapping is smooth, this mapping is smooth, meaning infinitely differentiable. Because if you verify that this mapping is infinitely differentiable, then the inverse looks exactly the same with A and B reversed, and so it's also going to be infinitely differentiable. Okay, so really what we have to do is we have to show that this thing is infinitely differentiable. Okay, well, again, I'm just going to chat my way through it. Okay. And so it's infinitely differentiable as a function of xb and vb. Okay, well, I know that this mapping is infinitely differentiable because it's the overlap mapping between two compatible charts. And similarly, I know that this mapping, not similarly, but identically, this mapping is infinitely differentiable. Okay, so therefore, its derivative is also infinitely differentiable, right? If you have an infinitely differentiable mapping, its derivative is infinitely differentiable. The degree of differentiability is infinity minus 1. which in this world of arithmetic, infinity minus 1 is equal to infinity. Okay, and so therefore this thing, as a function of xb, that thing is infinitely differentiable. Okay, but now we also have to consider this part, the function as a function of VB. Well, it's linear in VB, right? It's just, matrix multiplication. Okay, so what do I have? I have an infinitely differentiable matrix function multiplied by a vector. And so you have to show that that thing is infinitely differentiable, and you can kind of do that by just properties of the chain rule, for example. Okay, all right. So I will summarize that whole discussion by the following statement. Okay, and that finishes the fact that the tangent bundle of a manifold is a manifold, and I have an explicit atlas for it. So this isn't just all sort of hyperbole. We're actually going to be using this formula a lot to talk about things that have physical meaning. Okay, and so this proof is actually going to be helpful for us in understanding how to do various kinds of things as time goes by. And so there's going to be like a computational facet to the things that we're talking about, and this formula is going to play a key role in that. Okay, but that's all for the future. Okay, so we're going, as I said last time, and I'll say it again now, we're going to be spending some time on this. So if you weren't perfectly clear on everything that I did today, we're going to be revisiting this from multiple angles as time goes by, and hopefully it'll become clearer just what it is that you're supposed to take away from this. Okay, so this is going to be a bit of a process. Okay, so that's all I have for today. I will stop the recording.